Okay, this video is going to be about nuclear energy. I know there's been some requests for reviewing nuclear power plants and nuclear energy in general. So I'm just going to go through some of the PowerPoint slides that we went over when we did our nuclear energy chapter. The first thing that you need to be able to do is differentiate between nuclear fission and nuclear fusion. Nuclear fission is what we do in our nuclear power plants today. So this is showing you nuclear fission. Fission is when we have an atom, such as uranium-235, and the atom is going to split, releasing energy as heat. So that's nuclear fission. Nuclear fission is what we do today. Nuclear fusion is going to be, hopefully, the energy of the future. Nuclear fusion is different. We have not produced energy by nuclear fusion that we've been able to convert to electricity. But this is when we actually take two atoms and we fuse them together. So you can see the isotopes of hydrogen, which are deuterium and tritium. These can be forced together or fused together, and that's called nuclear fusion. And it releases immense amounts of energy. This is how the sun releases its energy, by nuclear fusion. So nuclear fission we do, nuclear fusion not yet. All right, so the first thing that you should know about nuclear fission is that we use uranium as the fuel source. So mostly uranium. Remember, uranium is a non-renewable mineral, and we have to mine for uranium. I'm pretty sure I told you that one of these pellets here, 1 kilogram of uranium, gives us the same amount of heat energy as 1 ton of coal. So we get a lot of energy from a very small source here. And these are very tiny pellets, and these pellets consist of uranium-238 and uranium-235. At least 3% U-235. Remember that uranium-238 is the most abundant, but U-235 is what we need in order to carry on a controlled chain reaction. So U-235 is the isotope that we need here. So this was the picture that we looked at from our textbook, and this is showing you a nuclear power plant, and you can see this is called a pressurized water reactor, a PWR. And in the United States, there are 65 pressurized water reactors, and there are 35 boiling water reactors. I'm going to show you a picture of that on the next slide. And just some information for you. In 2012, for the production of electricity, coal produced about 38% of the electricity, natural gas about 30%, and nuclear about 19%. So just about 20% of the electricity in the United States is produced through nuclear fission. So this is our nuclear power plant, and we're just going to go through the different parts. On the 1998 real exam, but you guys have access to it online, they asked an FRQ about a pressurized water reactor, and they asked the students to identify the different parts and basically to describe their function, so what each part did. And so I really don't think that they're going to ask you to do something that easy. That just seems too easy to me. But maybe they'll ask you always pros and cons with nuclear energy. It can be environmental, economic, so I'll go through those at the end. But just to go through the actual reactor itself, you can see the different parts. We have to start out with the containment building. This is the building that is around the nuclear reactor itself. It is used for protection. The building is very thick, can be made of concrete, and its main function is to protect anything from seeping out of the reactor core. So if there were some type of accident, that it kind of contains everything, and that's that containment building. The next area that I'm going to look at here is the reactor vessel. The reactor vessel is this whole thing itself, this like orangey colored thing, and this is called the reactor vessel. And so inside the reactor vessel, we have the reactor core. And you can see this is where fission takes place in the reactor core. We also have our fuel assemblies. So we have 3 fuel assemblies here. These are just long rods that contain the pellets, the uranium pellets. And we also have control rods. And control rods are used to start and stop the reaction. They're made of different metals like boron and cadmium. And the metals that are in the control rods will absorb the neutrons. So when the control rods are put down into the nuclear reactor, it's going to stop the reaction from taking place. And when the control rods are lifted out of the nuclear reactor, the neutrons are going to be able to bombard other uranium-235 atoms, and we're going to see fission take place. So the control rods start and stop the reaction. Then we have our circuits. We have three main circuits with our pressurized water reactor. We have our primary circuit, which is the orange color right here. And the water here stays under very high pressure, so it never changes to steam. That's why it's a pressurized water reactor. So the water stays in a liquid form, and it basically brings the heat from the reactor core over here to this steam generator, where the heat from the primary circuit, the orange coils here, is going to be transferred into the secondary circuit here. And so the water in the primary circuit stays in the primary circuit. It does not mix with the blue secondary circuit here, and it's just moving in a general direction. It's pumps, so there's a series of pumps that's moving this water. The secondary water circuit, this is where we have this water going to the steam generator, and this water is changing into steam, and that steam is going to turn the turbine that is connected to a generator to produce electricity. So this is where we're actually going to generate the electricity from the secondary loop here. And after that steam is used, it's going to be condensed back into a liquid form. So it's going to move back into a liquid, and then it's going to be cycled and pumped back to the steam generator, where there's going to be an exchange of heat, and then it's going to change into steam, then it's going to turn the turbine, produce electricity, and then that water is going to be condensed into a liquid. And this is going to happen over and over and over again. And then we have our tertiary circuit, our last one, where we have water coming in from either a lake or a cooling tower. Usually is associated if it's not along a coastline. So water will be brought in, and then the heat from the secondary circuit is going to transfer into the tertiary circuit, and now that water is going to be brought out of the nuclear power plant, essentially removing the heat from within the nuclear power plant. Remember that none of these circuits overlap, so the water that's leaving the nuclear power plant in the tertiary circuit is not radioactive. There's no radioactive isotopes associated with it, but that water is going to be removed, and there may be a cooling tower. So if you ever see a nuclear power plant with like a large tower and it looks like there's smoke or steam coming out, that's all it is smoke or steam. There are no sulfur oxides associated with this like there is with coal, and that's just removing the heat from within the nuclear power plant. If it's along an estuary, and I think I've said this a billion times, but for the nuclear power plants like up in Hutchinson, where it's along the ocean, this heated water will just go out into the estuary, and that's a form of thermal pollution. So if you had to talk about a type of pollution associated with nuclear energy, thermal pollution is an excellent example. And the reason why it's a problem is because it's going to decrease the amount of dissolved oxygen in the water. So any fish, manatees, whatever aquatic organisms that are lingering around the nuclear power plant, there's just going to be less oxygen for those animals to respire, and that could essentially kill fish. But this is basically what the nuclear power plant looks like. Some positives of nuclear energy. We have a decent amount of uranium, so but we also have coal. But we have uranium. You can see, like I said, we get a lot of energy from a small amount. For nuclear energy, you could say there's no air pollutants. That's one of the strongest arguments. So we are not releasing the sulfur dioxide that we're releasing with burning coal. We're not releasing mercury. A lot of the mercury in the environment comes from burning coal. So reduction in sulfur oxides, reduction in mercury, reduction in carbon dioxides into the environment. So we're really reducing air pollutants when we're using nuclear power. A problem with nuclear power, the biggest problem with nuclear power, is that we have to store radioactive waste. So after we're done using these uranium pellets in the fuel assemblies, or even just decommissioning or breaking down a nuclear power plant because it's been used for the licensed amount of time, which is 40 years, we have to put this stuff someplace for many times of like 1,000 years, because the uranium or this liquid, it can be radioactive for a very long time, and it can be dangerous. So we have to figure out where to put the nuclear waste that's associated with this primary circuit. And a lot of times when we talked about this, a lot of the nuclear waste is kept on site, either in pools, so there's these large pools that are kept at the nuclear power plants, underneath the water, and it helps to reduce the possibility of neutrons flying from one, I guess, pellet to another, therefore starting a chain reaction. So we put them on site in pools, or we can put them in above casks, like above ground casks, where they're just stored and guarded. Liquid from nuclear power plants can go through the process of vitrification, which is taking that liquid and making it into ceramic material. It's almost like ceramic, and it just makes it easier to store a solid material versus a liquid. Um, the other type of reactor that we have in the United States, and the one that actually was involved in the Fukushima disaster, was a boiling water reactor. So it's a little bit different, but not overly different. And you can see here the main difference is that the water in the primary circuit, what would be the primary circuit for your pressurized water reactor, instead of it staying in a liquid form under high pressure, in a boiling water reactor, that water is actually changed into steam. So we have that water coming into contact with the reaction itself, and that water is actually going to change into steam, and then that steam is going to turn the turbine to produce electricity, and then it's going to be condensed back into a liquid form, and then that liquid's going to go back to that reactor core, again, change into steam. So the pressurized water reactor, it's very similar, but it's just going to stay as water in that primary circuit. So the way that it works, and this was the slide that I showed you guys, U-235 is bombarded with neutrons. When the nucleus is struck, it's going to absorb the neutrons, and U-235 will become unstable and split. 2 to 3 neutrons are ejected from the atom, causing a controlled chain reaction. And basically, we're looking for that heat, the energy as heat, and then we're going to use that heat to make electricity. Something different, breeder nuclear fission. We don't do this in the United States, but other countries do use breeder nuclear fission. Notice here that instead of uranium as our isotope that we're using, they are using plutonium. So plutonium-239 is used for breeder nuclear fission. And plutonium can be made from uranium-238. So uranium-238, which 99% of our uranium is made up of this isotope of 238, can actually be made into plutonium, and then plutonium is going to be the fissionable material here. So a neutron's going to hit plutonium. Again, we're going to release neutrons. We're going to have a chain reaction here, and heat's going to be released. But the interesting thing about breeder nuclear fission is that you're actually going to produce some fuel. So because when we hit this plutonium atom with a neutron, this neutron will be absorbed, actually producing more uranium-238, and we actually are producing fuel with breeder nuclear fission. We don't do it here. Plutonium is considered weapons grade and used in nuclear weapons, so we really shy away from using plutonium. Breeder nuclear fission, the positives, it produces more fuel than it actually uses. Some of the negatives associated with it is that, again, you're producing this high-level radioactive waste, and also can be dangerous. So in that primary circuit, instead of using water, many times they use liquid sodium, which can be very explosive if it were to come into contact with oxygen or water or anything else. If there was like a crack in a pipe, it can be explosive. And I think, oh, and nuclear fusion. Let's see what we have for nuclear fusion. Here we have nuclear fusion. Again, we use nuclear fission. So currently we produce electricity from nuclear fission. One day maybe we'll use nuclear fusion. Could be the way of the future. Benefit of using nuclear fusion, again, this is when we're taking the isotopes of hydrogen, deuterium, and tritium, and we're fusing them together. It uses very high temperatures to force them together, and we're going to release immense amounts of energy. So this is a difficult reaction to control. You're actually producing no high-level radioactive waste, so it would take care of that disposal problem that we have with nuclear fission. The fuel is hydrogen, so we have abundant hydrogen fuel. That's not going to be a problem. But some of the problems associated with it, very high temperatures, millions of degrees to make atoms fuse. So it's very difficult to control the reaction at very high temperatures. And plasma tends to expand. How are we going to confine the plasma? Again, this is all because of the very high temperatures that we're using in order for this reaction to take place. And it says scientists have yet to be able to create energy from fusion. We talked about the tokamak, which is in France currently, and at some point maybe we'll be able to produce energy from nuclear fusion. So, okay, that is my nuclear video.